In my quest to get the annual Focusrite student placement next year, I'm on a mission to complete one product every month, or at least try to. And what better way to start off products for an audio software company than to analyze the basis of all audio itself, the sine wave. Mathematically, sine is just the value we get if we want to know how high up the point of a rotating vector is around the unit circle, which also falls back on the idea of why if we have the angle of a right angle triangle, using sine and hypotenuse would give us the length of the side analogous to the y-axis on a graph, which is, well, the opposite side. In a past video, I go over how if you were to plot these values over time, you get the usual sine wave representation that we all know and love. But today I want to ask the question, how does a computer even know what this length is when putting in the angle? Or in other words, when you input an angle into sine on a calculator, how does it know what the output should be? Moreover, is this something that could be performed on hardware dating back decades before I was born? Well, the algorithm was. The algorithm is ancient. The usual method to solve this problem is a lookup table, where pre-computed values for sine are already made, and all the computer has to do is just treat the incoming angle as an index into that table. If the angle we gave points to the index that has the value of 1 in it, it's highly likely that we inputted 90 degrees or pi divided by 2 radians. If we then input an angle that produces an index that isn't a whole number, and so the computer can't really point to a definitive location, we can interpolate the values that are close and that we can actually point to. If the index turns out to be 3.5, for instance, if we take the value at index 3 and the value at index 4, then find the midpoint of those two values, we're effectively finding what the value at 3.5 should be, and so we can use that. Like I said, this is the usual method that many applications use, and if you've ever wondered, this idea is exactly what a wavetable for your favorite synthesizer VST actually is. Instead of the values following those of a normal sine wave, it just follows whatever it wants to as long as it's periodic. And even sine waves in those VSTs are actually lookup tables and wavetables themselves. The only problem is these tables can, in certain spaces, take up a lot of memory. Not to mention, to carry out the interpolation needed to find the intermediate values for non-integer indexes, we need access to a system that could both multiply and divide. In modern day systems, these usually aren't concerned since we have more memory than we even know what to deal with, so we use it to make fake art, and multiplication and division is something built into almost everything we use. And yet, still, there's a method that is able to compute sine and cosine at the same time, bypassing all of those issues. And that's where the quadratic algorithm shines. Quadratic, or coordinate rotation digital computer, works as the name describes. We start off with a vector that represents the input angle that we originally gave to the calculator, and then what we do is we create another vector and iteratively rotate that other vector until it lines up with the input vector that represents our angle, thereby finding the right coordinates for both sine and cosine, or y and x respectively. I just want to record this part to say that technically this input vector doesn't really exist, but because we're doing more or less a binary search based on the rotation angle, we are kind of lining up with a vector. And it will always converge to that right angle, to that vector, and then we can find out what sine and cosine is. Again, it's like binary search, where we just keep on getting closer and closer and closer if we find out if we're higher or lower. That's essentially what this algorithm is doing. Without going into any detail just yet, you may already be thinking that starting off we need to have something pre-computed to have as our basis of rotation, and you'd definitely be right. Ironically, while this method is hailed as the alternative to lookup tables, we still do need one for this to work, albeit of a different nature and being nowhere as big compared to if we were using it to store sine values. In fact, by the end of this video, you'll see how close of approximation we can get just by using a lookup table with only 7 values in it, and on a microcontroller that is only 8 bits. Introducing the PIC16F877A. This is the chip I used for school last semester, and it is a microcontroller that only has 8 bits to store memory in. To add even more limitations, we can only add, subtract, increment, decrement, and shift values. There is no built-in multiplier, no division, and, well, something I haven't actually touched on just yet, no floating point values. If you're familiar with some coding or computers in general, you may know that the fractional values are usually referred to as floats or floating point values. And these fractional values are managed by previously stated floating point units that our picker does not have, which For a function that more often than not gives us fractional values as an output, or dare I say it only gives us fractional values apart from only 4, which is, positive 1, negative 1, 0, really only 3, you can see this is a bit of an issue. Luckily for us, floats aren't the only representation of fractional values. In fact, they are actually even more confusing and convoluted, which is why we need whole units to actually work through them. Instead, we can use fixed point values, where with our 8-bit microcontroller, we can use a few of those bits to specifically represent the fractional part for our number, and the others can just be the whole integer value. The more bits we give either side specifies how precise we can get for each one, but since sign never goes above an integer value of 1, we can relegate our integer part to only being 1 bit and having 1 extra bit at the end to be for the sign. Thereby, we're having a value of 6 bits to represent our fractional part, which is not that big, but as you'll see, will still actually work. We'll see exactly what this all means during the implementation part, but before that, let's take a look at Cordic once more. I'm actually not going to explain this algorithm in depth like I did with other math concepts, mainly because my focus today is on the implementation, and also because there are resources abound that give way better explanations than I probably even could. Case in point, this video here that almost explains Cordic from first principles, not to mention this article here, and this GitHub article, which was the main source that actually made me understand what this algorithm does and gave forth a magical piece of pseudocode that was implemented in pick assembly. Notice the lack of multiplication, sine, and cosine values, meaning on something that can just add, subtract, and shift, this will work perfectly. Still, as a bit of an overview, like I said, we're constantly rotating a vector either clockwise or counterclockwise, depending on the sign of a certain z variable. If we're positive, we rotate counterclockwise. If we're negative, we rotate clockwise, which makes sense. Imagine either going up or down. The mathematical expression that defines each rotation is here, which can then be rewritten as so. Again, these resources explain how we can get there algebraically, but the issue still arises with having to multiply these tan thetas and this outward cosine theta. In fact, we're trying to figure out how to work out cosine, so having to use cosine to figure out cosine isn't really for the best, is it? That being said, each theta represents the rotation angle we're currently doing, and so it updates after each iteration. We can then choose those angles specifically in a way that each time for tan theta, we get an inverse power of 2, meaning that multiplication by them is just a bit shift. In binary, if we had the number 0010 or 2 and shifted all the numbers to the left, we're multiplying that value by 2 to the power of the number of shifts we do. If we did one more shift, meaning we would have an overall of 2 shifts, we'd be multiplying that value by 2 to the power of 2, or 4. The original value was 2, and 2 times 2 to the power of 2, or 4, is 8, which is exactly the value that we currently have. Thereby, if each angle we gave to tan was a tan 2 to the power of negative I, with I being our index, we'd always get an answer that is just a power of 2. On paper, this is actually great because we don't really need to worry about what this a tan 2 to the power of negative I is if we just critically think about how many powers of 2 we need. But unfortunately, we still have to calculate them. We still do need to know which direction each angle needs to rotate in. And thus, if we had the angle value and subtracted it from the target angle, if the value we get after that is negative, we know that we're at a point that is bigger than the target value and we need to backtrack. If it's positive, we know that the angle is smaller and we need to keep on going up for the next rotation. So we need those values, and we can only do that by pre-computing. Again, I said that we can't completely escape it, but we only need 7 values. The number of values that we need really correlates with how many bits we're using to showcase the fractional part. After a certain point, the values zero themselves out and you would get no difference essentially. So again, you really only need 6 really, but I'm just gonna do 7 just because, you know. And so now, knowing all of this, if you get how matrix multiplication works, you can see how this then becomes this, where each iteration, we check to see if we're rotating clockwise or counterclockwise. We get a new value from the lookup table to facilitate this, and we do our bit shifts based on indexes accordingly to substitute for multiplication. The only issue is this cosine theta that's left right outside here. To do a little bit more math hand wavy, just know that if we multiply all these cosines that we do for each angle rotation, they all converge to a single constant, which is great because now we only have to worry about one big multiplication that we can do at the end of the algorithm, then having to do a multiplication on each iteration. We could also just then pre-compute that value and do the multiplication after the fact. Or we could do it at the beginning as well. If we started out on the values of cosine being 1 and sine being 0, which means that our vector here is just lying on the x-axis, x is 1 and y is 0, since cosine is 1 and sine is 0 respectively. If we multiply this constant to both values, we still get 0 for sine, and the value of x will then become that constant. So instead of worrying about multiplying everything by the value at the end after the fact, if we just set x to be that value, it acts as us multiplying it at the beginning, which means that we've already correctly scaled our vectors and no multiplication that isn't a bit shift is needed at all, which is great. And so now implementation, which is what I wanted to showcase in the first place actually. We only have 8 bits on our pick, which even for a tried and true algorithm like this, still isn't enough to get great precision. But it is still impressive how much precision we do actually get. Allocating 7 bits to be our fractional part and 1 bit to be our sine seems intuitive, as the output of sine and cosine can never be above 1 or below -1. But we are running on approximations, and with this setup, we unfortunately don't actually even reach +1. Not entirely. So it's not recommended, even though maybe some technicalities could work, but you probably shouldn't do it. So having 6 bits for our fraction, 1 bit for our whole number, and 1 bit for the sine does make the fractional precision even less, but we can actually fill out the desired range without also worrying about potential overflow, all that kind of stuff. So with that in mind, we represent everything using that format. So any whole number would have to be shifted up 6 times to actually represent that number. And same goes for all the fractional values as well. The target angle is converted by having it in radians first if it isn't already, and multiplying it by 2 to the power of 6 or 6 bit shifts. The constant that we start off x with is calculated as well, and also multiplied by 2 to the power of 6 or 6 bit shifts. And we can assign each variable accordingly. Saying that 39 is equal to 0.60725 might seem weird at first, but remember, computers only see 1s and 0s. Even though this value by itself is 39, we as the programmer must assign it the meaning of 0.60725. It is also an approximation, by the way, since the actual answer when you multiply by 64 or 2 to the power of 6 is 38.864, but we can't actually represent that like I said, so we only have integer values to work with. We're rounding it up to be 39, which is the value that we can actually use. And with all that legwork in place, if the angle we're using is 45 degrees, we make our initial calculations and let the algorithm do its rotation, depending on if z is positive or negative. And finally, for our pick example, we get the value of 46 for y or sine, and 44 for x or cosine. We're still in our fixed point format, thus to go back to our original decimal, we divide that answer by 64, hence why it looks like that on the LCD, and we get the values of 0.718 and 0.687. Using the built-in calculator's sine and cosine functions, each value gives us 0.707, which makes sense since it's the midpoint between 0 and 90 degrees. But these values are still pretty close. It's not perfected, but again, we only really had 8, dare I say 6 bits to work with. When in a usual modern day C program, yes, C, the usual integer has 32 bits in it. 4 times the number of bits that we have, and even more times the precision. So we're not actually doing that bad. Thanks to how we split up all the bits, we can in fact still represent values that range from 0 to -90 degrees. And we can actually represent values on the second and third quadrant as well if we do a little bit more work. It does suck, however, that for an algorithm that prides itself on no multiplication, we do have to do a bunch of multiplication beforehand, but I'm sure there's other algorithms out there that make the conversion from degrees to fixed point radians, as an example, work on a system as minimal as this. And you could also tweak this algorithm to compute a range of other trigonometric and even logarithmic functions as well. But I'll leave that for if this video actually gets engagement. Like I said, there are resources to further your studies on this algorithm, and a run through of the code I made, as well as how I got it to display on the LCD screen. That can be found on my Patreon as well. If you just want the source code, it'll be available once the next video comes out, which if I keep on schedule should be in like a month or two, if you're willing to wait.